Complex analysis, practice final exam part 3, picking up with number 7. We're going to let U of x, y be harmonic on a simply connected domain where omega is a subset of C. Okay, so part A, B, and C. So part A, prove that U has a harmonic conjugate on omega. Sorry for my poorly drawn omegas. Part B, give an example showing why simple connectedness is necessary. And part C, for U of x, y equals log the square root of x squared plus y squared, defined on the complex plane with 0 removed. Determine whether a single valued harmonic conjugate exists. Okay, so harmonic functions problem. So we're going to let U be harmonic on a simply connected domain omega. Define the differential form. W equals negative U sub y dx plus U sub x dy. And a harmonic conjugate V should satisfy the Cauchy-Riemann equation. So V sub x equals negative U sub y, and V sub y equals positive U sub x. So dV equals negative U sub y dx plus U sub x dy. And the form W is closed because this partial respect to y of that negative U sub y, that equals negative U sub yy. And this partial with respect to y of negative U sub y, that equals negative U sub yy. I wrote that twice. Sorry about that. And partial respect to x of U sub x equals U sub xx. So since U is harmonic, U sub xx plus U sub yy equals 0. So negative U sub yy equals U sub xx. Thus we can conclude for that part W is closed. And on a simply connected domain, every closed form is exact. Therefore, there exists V such that dV equals W, so V sub x equals negative U sub y, V sub y equals U sub x. So F equals U plus IV is holomorphic. And therefore, we could say U has a harmonic conjugate on omega. For an example, showing simple connectedness matters, we're going to take U of x comma y equals log square root of x squared plus y squared. That's going to be log of absolute value there of z on the complex plane with 0 removed. And a local harmonic conjugate is V equals ARGZ. However, ARGZ can't be chosen continuously and single-valuedly on all of a complex plane with C removed. So for the given U, no global single-valued harmonic conjugate exists on the complex plane with 0 removed. Okay, so that's number 7. And we're moving along now to number 8. So let F be holomorphic on a connected domain omega, and suppose absolute value of F has a local maximum at the same point here. Z naught belongs to omega. Okay, so part A, prove that F is constant. Part B, explain how this result follows from open mapping theorem. And part C, give an example showing that the conclusion fails if F is merely smooth rather than holomorphic. Okay. So this is a maximum modulus and open mapping problem. So for part A, we suppose absolute value of F has a local maximum at Z naught belonging to omega. And if F of Z naught equals 0, near Z naught, modulus F of Z is less than or equal to that modulus of F of Z naught is equal to 0. So F equals 0 locally. And by the identity theorem, we have the following relating F and 0. And if F of Z naught does not equal 0, then 1 over F is holomorphic near Z naught. Since absolute value of F has a local maximum, absolute value of 1 over F has a local minimum. And equivalently, one can apply the maximum modulus principle directly. A non-constant holomorphic function cannot have an interior local maximum of its modulus. So f is constant. And moving along to part B, explain how the result follows from the open mapping theorem. So part B, using the open mapping theorem, if f were non-constant, then f of omega would be open. But if absolute value of f has a local maximum at z naught, then near f of z naught here, the image cannot contain points, okay, of larger modulus, so that contradicts openness. Hence, f must be constant. And for a harmonic counterexample, if we wanted to let u of xy equal 1 minus x squared minus y squared, we can say that this is not harmonic because delta u is negative 4. So if we instead take u of xy equals x, but this will wind up with x has no interior local maximum. So into letter C, giving an example showing that the conclusion fails if f is merely smooth rather than holomorphic. So just building on this, what we could say is for a smooth non-holomorphic function, the conclusion fails. And for example, g of z equals 1 minus absolute value of z squared, has a strict local maximum at z equals 0, but it is not holomorphic. Okay, so that's letter C, and that's all for 8. Let's move along now to number 9. Sorry about the delay. Okay, unit disk here. So let the family here, let f be the family here for this problem of homomorphic functions on that unit disk. D, satisfying here this absolute value of f of z is less than or equal to 1 over 1 minus absolute value of z for all z belonging to the unit disk D. Part A, prove that f is a normal family. Part B, does the family have a uniformly bounded does the family have to be uniformly bounded on all of the unit disk? Explain. And part C, show that every sequence in F has a subsequence converging uniformly on compact subsets of D. So normal families problem. So for each compact set here belonging K in the disk, unit disk here, there exists R as less than 1 such that K is that subset there of absolute value of Z less than or equal to R. And for Z belonging to K, modulus of f of Z is less than or equal to 1 over 1 minus absolute value of Z is less than or equal to 1 over R. So therefore, f is uniformly bounded on every compact subset of D. And now here, by Montel's theorem, f is a normal family. It does not have to be uniformly bounded on all the unit disk because 1 over 1 minus absolute value of z blows up as the absolute value of z goes here. So for example, the constant functions f sub n of z equal n do not satisfy the bound on the whole disk. But one can construct functions whose sizes grow near the boundary while still obeying the given estimate. And the key point is that the normality only requires local uniform boundedness on compact subsets, not global boundedness on the full domain. So every sequence here, given here, has a subsequence converging uniformly on the compact subsets of the unit disk to a holomorphic limit, or in the broader spherical sense to a meromorphic limit. And since the family is locally uniformly bounded in the ordinary complex plane, the limit is holomorphic. So concluding here, every sequence has a subsequence converging uniformly on compact subsets to a holomorphic. Okay, so that is all for part 3. Thank you very much and have a great day.